My name is Billy Sedberry, and I am a member of Team Thunderstrike, and I will be presenting to you today about Hendy's Law, developed by Barry Hendy of Kodak in Australia. When Barry Hendy was an employee at Kodak of Australia, he noticed that the amount of pixels that digital cameras had were increasing over time, and the amount of pixels that you got per dollar was also increasing. So to put it another way, the same 1.0 megapixel camera got cheaper year after year, or for the same $100 each year, you would be able to buy a better camera. Each year, digital cameras were getting sharper and better, and the most primary factor in the improving image quality was the increasing number of pixels. While there are other factors that go into image quality, pixel count has always traditionally been the main factor. The trend that Barry Hendy noticed is similar to how computer processors get faster and faster each year. This is already known as Moore's Law. Moore's Law is named after Gordon Moore, who is best known as co-founder of Intel, the manufacturer of computer processors. Moore's Law states that the number of transistors on an integrated circuit doubles approximately every 2 years. Integrated circuits are what replaced vacuum tubes and are used in almost every electronic device you own. Gordon Moore first described this phenomenon in 1965, and the term Moore's Law was first coined in 1970 by Carver Mead, a professor at Caltech University. Just 5 years after Gordon Moore first made his observation, it was already considered a law, and the trend is still on track to this day and even considered an industry standard. Because integrated circuits are used in so many things, other electronic devices are also increasing at the same pace, such as memory size, storage capacity, as well as processing speed, and of course, the number of pixels in a digital camera sensor. When Barry Hendy was working at Kodak, he noticed that the amount of pixels in a digital camera sensor was increasing all the time. He also noticed the cost was decreasing relative to pixel size. Barry Hendy went to work on this notion and researched the whole market for digital cameras, finding out just how many pixels per dollar you can get each year based on various cameras for sale at any given point in time. As you can see, the result has the same similar trend as Moore's Law. The difference is that when we talk specifically about the increasing number of pixels, then we're referring to Hendy's Law. In the graph, you can see where we started with the Kodak DCS-460, which is a 6.2 megapixel camera, and then we move along the graph and stop in 2005 with the Kodak C310, which is actually only a 4 megapixel camera. The difference is that to get 6 megapixels in 1994, you're basically going to be buying an expensive professional grade camera such as a DCS-460. When you fast forward to 2005, you can just buy a cheap little pocket camera such as the C310 and you still get a large megapixel count. It's easy to look at Hendy's Law and assume that megapixel count is the only factor in picture quality, but that is not necessarily true. Digital cameras still have many parts in common with traditional cameras, and these still play a factor in image quality. If we think about Hendy's graph not just as pixels per dollar, but image quality per dollar, we can draw a correlation to all cameras, not just the digital cameras. Cameras in general have advanced from simple pinhole brownie cameras to color cameras, and even Polaroid instant film cameras. All the while, each technology has become cheaper along the way as time has progressed. Digital cameras are similar to regular cameras except that they replace the film with a CCD or charge-coupled device sensor that senses the incoming light. Because digital cameras still share many parts with traditional cameras, many of these same rules still apply. If you have a small lens and a small film size, then there is not enough light to make a good image within a given exposure time. The best cameras traditionally have had large lenses and use large film formats. This allows much more light to reach the film to produce an image in that tiny fraction of a second that the shutter is open. The same basic principle still holds true with digital cameras, except with some twists. One interesting factor with digital cameras is that the individual pixel size on the camera's sensor can be so small on modern cameras that it's difficult for enough light to hit the sensor during a given exposure time. Modern cameras are actually reaching a hard theoretical limit on how small you can make the pixels and still be usable. This is where sensor size becomes an important factor in image quality. By sensor size, we do not mean megapixel count, but rather the physical dimensions and square area of the sensor. For example, Canon has a 4 megapixel point-and-shoot pocket camera, and each pixel only covers 3.1 square microns. The Canon D60 is a 6.4 megapixel camera, but it uses a large format sensor, and each individual pixel covers 74 square microns. Sony makes a small, cheap point-and-click camera that is 16 megapixels, and they also make an expensive Alpha NEX, which is also 16 megapixels, but it uses a large APS-C format. The sensor on the small camera is comparable to a pinky fingernail, whereas the sensor on an NEX is closer to a large postage stamp. Having much more light hitting the sensor will produce much better pictures, just like using a large lens and a large film format. Here you can see on the left that when you use a camera with a physically small sensor, the camera compensates for the lower amount of light reaching the sensor. And it does this by amplifying the signal, and this creates digital noise. There is also less color reproduction. But if you use a large sensor, then this results in more light triggering the sensor and less amplification to the signal and less noise in the image. Here we see the same image on the left from a compact sensor, and on the right is a large format APS-C sensor. The larger sensor makes a clear difference. When we zoom into a darker area of the picture, we can begin to see the digital noise that is introduced via the amplification process in the camera. So if you are looking at digital cameras, don't just look at the megapixel count, but also consider that the actual size of the sensor will be a large factor in the overall image quality, especially in low light conditions where you need to use every last photon available that's coming through the lens. Another twist with digital cameras is that they don't have to have a shutter. Digital cameras are able to record the image quickly, much like film, but on some cameras the actual individual pixels are read line by line instead of all at once when a shutter opens and closes. If you have a cheaper camera that is shutterless, such as a smartphone camera, and you are taking shots of a fast-moving object, some strange effects can occur. This photo of an airplane propeller now looks like it has horizontal or vertical lines where the propeller was, depending on which way the camera was held. This effect is similar to holding a picture down on a flatbed scanner and then moving the picture around as the scan is recording. Now that the CCD pixel density is reaching the theoretical limits, camera engineers are looking for future technology and thinking outside the box to increase camera image quality. The inside of camera bodies and camera lenses must be completely black in order to absorb any stray light that is not being focused directly onto the camera sensor. One new technology that is being proposed comes from the world of carbon nanotubes. Scientists at the Rensselaer Polytechnic Institute have come up with a coating that is described as a forest of carbon nanotubes that has the ability to absorb 97.5% of light across the visible spectrum, and even some of the light in the infrared spectrum as well. Once this coating is used inside cameras and light detectors, there will be even less optical noise and even better image quality. Another new twist for digital cameras is a product called the Litro camera, a camera that allows you to shift the focal point of your photo after you have taken it. It uses light field technology to record in 3 dimensions every angle of light that is coming in to allow refocusing the shot after it has been taken. It also allows for 3D shots to be taken from one lens. Another advantage is that it has an instantaneous shutter that is usually only found on more expensive cameras. Since the invention of the integrated circuit, our electronics have been getting better, faster, and smaller. We generally know this as Moore's law, but Hendy's law is used when we are referring specifically to pixel count. Just keep in mind that pixel count is no longer the only factor to consider when shopping for digital cameras, but actual sensor size is important as well.